In this class, I will solve two numerical examples using NTU approach for a counterflow heat exchanger. NTU approach is very effective tool in problems when exit temperatures of both fluids are not known. Let us solve a numerical example. A counterflow concentric tube heat exchanger with an overall heat transfer area 12 meters square is used to cool engine oil available at 100 degrees centigrade using cooling water available at 20 degrees centigrade. If the flow rate of oil and water are 2 kg per second and 0.5 kg per second respectively, find the outlet temperatures of oil and water and rate of heat transfer. Take U overall heat transfer coefficient as 400 watts per meter square Kelvin and Cp of oil 2000 joules per kilogram Kelvin and Cp of water as 4170 joules per kilogram Kelvin. Now you are given the inlet temperature of oil. So the purpose is to cool engine oil which is coming into the heat exchanger at 100 degrees centigrade using cooling water which is entering at 20 degrees centigrade. So both inlet temperature of hot and cold fluid are known, but both outlet temperatures are not known. Area of the heat exchanger is given as 12 meters square. So it's a concentric tube counterflow heat exchanger. The flow rate of oil and water are 2 kg per second. So oil is a hot fluid here. So oil flow rate means mH is 2 kg per second and water flow rate is 0.5 kg per second. That is mc. Overall heat transfer coefficient is given. Cp value of oil is given. Cp value of water is given. Now in this case you can easily see that NTU approach is going to be easy for us because outlet temperatures of both the fluids are not known. So LFTD method become tedious. Area is given as 12 meters square. Inlet temperature of hot fluid is known 100 degrees centigrade. Cold fluid it is 20 degrees centigrade. Mass flow rate of hot fluid is 2 kg per second. Mass flow rate of cold fluid, that is water, 0.5 kg per second. Cp of hot fluid is 2000 joule per kilogram Kelvin and CPC, that is for water, it's 4170 joules per kilogram Kelvin, and overall heat transfer coefficient is 400 watts per meter square Kelvin. So these are the data given. Now from Cp value and mass flow rate you can calculate the heat capacity of both the fluids. CH is mHCpH and mass flow rate of hot fluid, that is for oil flowing at the rate of 2 kg per second, and its Cp value is 2000. So you get 4000 watts per Kelvin as heat capacity of hot fluid. Now heat capacity of cold fluid is mCCpC. So mass flow rate is 0.5. Cp value is 4170. So we get the heat capacity of cold fluid as 2085 watts per Kelvin. So out of these two values, this is minimum value of C heat capacity. So Cc is C minimum. Cc is minimum value. So Cc is C minimum 2085 watts per Kelvin. And Ch is now C max 4000 watts per Kelvin. Now you can find out NTU as using the equation UA by C minimum. U is known 400, area is 12, and minimum value of heat capacity is 2085. So you get NTU as 2.302. And the heat capacity ratio C minimum by C max is 2085 divided by 4000. You get 0.5213. Now for effectiveness of a counterflow heat exchanger, we have the expression 1 minus e raised to minus NTU into 1 minus C divided by 1 minus C into e raised to minus NTU into 1 minus C. We already calculated NTU and the heat capacity ratio. So you can substitute NTU value and heat capacity ratio in the expression and you will get the effectiveness as 0.8077. That is 80.77% is the effectiveness of this counterflow heat exchanger. Now we also know that effectiveness is actual heat transfer divided by maximum possible heat transfer. If you express actual heat transfer in terms of heat loss by hot fluid, you will get the numerator as Ch into Thi minus Th0 divided by C minimum into Thi minus Tci. Effectiveness is already known, so you can substitute for effectiveness. Ch in this case is 4000 and C minimum is 2085. And we know that inlet temperature of hot fluid and cold fluid. So if substituting that, you get the outlet temperature of hot fluid as 66.32 degrees centigrade. We can also find the effectiveness as heat gained by cold fluid divided by maximum possible heat transfer. Now the heat gained by cold fluid is Cc into Tc naught minus Tca divided by maximum possible heat transfer is C minimum into Thi minus Tca. Now in this case Cc is C minimum, so that will cancel out and you get the effectiveness in terms of temperatures. So effectiveness is known 0.8077. Inlet temperature of cold and hot fluid both are known, so you can substitute for inlet temperatures of both the fluids and you can solve for Tc naught. You get Tc naught as 84.62 degrees centigrade. Now to find out the heat transfer, you may use equation for heat lost by hot fluid or heat gained by cold fluid or heat crossing the boundary of the heat exchanger wall. So you can use Ch into Thi minus Th naught or Cc into Tc naught minus Tca or Q is equal to Ua into LMTD. Since in this case all four temperatures are known, even Ua into LMTD will give the heat transfer, since you can easily find out the LMTD as all four temperatures are known. I'll use heat loss by hot fluid as equation for calculating the heat transfer. So Ch is known, Ch is 4000 and Thi and Th naught both are known. Th naught we have calculated, so it is also known. Now substituting that, you will get the heat lost by hot fluid as 134,720 watts. Now converting this into kilowatts, you have to divide by 1000. After dividing by 1000, you will get the Q as 134.72 kilowatts. So this is the heat transfer in the heat exchanger, or it's the heat lost by hot fluid or heat gained by cold fluid. Let us work out another example. In a counterflow shell and tube, single pass steam condenser, cooling water flowing inside the tubes enters at 20 degrees centigrade. The tube has inner diameter 1.35 cm and outer diameter 1.6 cm. The velocity of water flowing inside the tube is 1.5 meter per second. Steam is condensing outside the tubes at 80 degrees centigrade and the heat transfer coefficient is 12,000 watts per meter square Kelvin. If there are 60 tubes each of 8 meter length and the tube wall thermal conductivity is 110 watts per meter Kelvin, find the rate of condensation of steam. So it's a shell and tube heat exchanger and single pass. Single pass means in the shell side the fluid is flowing through the tubes in the shell only once. It is not returning through the shell again. So only once from left to right just goes in one pass. So it is a single pass steam condenser and you have 60 tubes. But we can study single tube. What is the heat loss from a single tube? Like a normal tube-in-tube heat exchanger. From a single tube you can find out the heat transfer and then multiply with the 60, which will give the total heat transfer in the shell and tube heat exchanger. So one tube only you can analyze and find out the steam condensed over that tube and then multiply by 60, which will give the total steam condensed. So analysis is same because it's a counterflow shell and tube heat exchanger. That is, fluid is flowing in opposite direction. So you have to use the expression for counterflow heat exchanger. The difference between shell and tube and concentric tube is there are number of tubes. But in this case, we analyze only one tube. One tube we analyze and then find out the heat transfer by considering all the tubes. You are given the TCA. TCA is given. Thi and Th naught are same because the steam is condensing outside the tubes at 80 degrees centigrade. So Thi is and Th naught both are 80 degrees centigrade. The tube has inner diameter 1.35 cm and outer diameter 1.6 cm. And the velocity of water inside the tube is given 1.5 meter per second. Outside heat transfer coefficient is given outside the tube. Steam is condensing outside the tube and heat transfer coefficient on the outside is given as 12,000 watts per meter square Kelvin. The tube length is given here and there are 60 tubes and the thermal conductivity of tube wall material is given 110 watts per meter Kelvin. So you have to find out the rate of condensation of steam. So here the main problem is you are not given the overall heat transfer coefficient. So to find out the overall heat transfer coefficient, outside heat transfer coefficient is given, but you are not given the inside heat transfer coefficient. And thermal conductivity of the pipe material is given, and the diameters of the inside and outside diameters of the pipe is given. So you have to first calculate the overall heat transfer coefficient. So once you calculate the overall heat transfer coefficient, the other procedure is same. You can approach by NTU method and solve the problem. So first challenge is to find out the overall heat transfer coefficient. and we have already seen in the first video how to obtain the overall heat transfer coefficient, the equation for overall heat transfer coefficient. If you know the inside heat transfer coefficient, the outside heat transfer coefficient, and thermal conductivity and other properties are known, how to find out the overall heat transfer coefficient. Even the data handbook, you can find out the expression. You just familiarize with the data handbook. Let us tabulate the given data. Inlet temperature of hot fluid is 80 degrees centigrade. Outlet temperature is also 80 degrees centigrade. Inlet temperature of cold fluid is, that is water, is 20 degrees centigrade. H0, outside heat transfer coefficient, is 12,000 watts per meter square Kelvin. Velocity of water in the tube is 1.5 meter per second. Inside and outside diameters of the tube converted into meters, 0.0135 and 0.016 meter. Length of the tube is 8 meter. Thermal conductivity of the tube wall material is 110 watts per meter Kelvin. Now, to find out the inside heat transfer coefficient, you are given the velocity and the diameter of the pipe where fluid is flowing. So, through this inner, say inside the tube diameter is 1.35 centimeter. Through this tube, water is flowing at 1.5 meter per second. So, you have to use some convection correlations to find out the inside heat transfer coefficient. So, commonly used correlation for getting it is Nusselt number is equal to 0.023 Re raised to 0.8 Tr raised to 0.4. It's a Reynolds number and Prandtl number. For fluid flow inside the pipes, this is the equation which is commonly used to obtain the heat transfer coefficient. And here, since the fluid flowing inside the pipe is getting heated, we have used the index as 0.4. If it is getting cooled, if the fluid is getting cooled, we use 0.3. Now, to find out Re and Pr, that is Reynolds number and Prandtl number, we need to refer the data handbook. Reynolds number, you need to calculate either Vd by nu, that is velocity into diameter of the pipe divided by kinematic viscosity, or Ovd by mu. Mu is a dynamic viscosity. So, I use Vd by nu. Mu is the kinematic viscosity, V is the velocity, D is the diameter. This Prandtl number directly you can get from the data handbook. And here Nusselt number is HL by K. L is a characteristic length, but in this case characteristic length is diameter itself. So, inside diameter. And K is thermal conductivity of the fluid, not the thermal conductivity of the pipe material. Thermal conductivity of the fluid. Here the water is flowing inside the pipe. So, water thermal conductivity at the given temperature 20 degrees centigrade you need to get from the data handbook. So, first you have to refer the data handbook. At 20 degrees centigrade, that is the inlet temperature. We don't know the outlet temperature. If outlet temperature is also known, you can take the average temperature. Inlet temperature plus outlet temperature divided by 2. That average temperature you can find out the properties. But in this case, we know only the inlet temperature. So, based on the inlet temperature, you can find out the values of fluid properties, that is water, properties of water. This you can get it from the data handbook. So, Cp value of water at 20 degrees centigrade is 4178 joules per kilogram Kelvin, and density of water 1000 kilogram per meter cube, and thermal conductivity of water at 20 degrees centigrade is 0.5978 watts per meter Kelvin. Kinematic viscosity is 1.006 into 10 raised to minus 6 meters square per second, and Prandtl number is 7.02. And also you can get the enthalpy of evaporation of water at 80 degrees centigrade. At 80 degrees centigrade, when the water is saturated at 80 degrees centigrade, what is the enthalpy of evaporation? You can get it from the steam tables, and it is 2645 kilojoule per kilogram. So, converted into joules per kilogram, you have to multiply by 1000. So, after getting all this data, you can use the standard correlation and then substitute for the values. Velocity is 1.5, diameter is inside diameter, it is 0.0135, and new kinematic viscosity 1.06 into 10 raised to minus 6. Prandtl number is 7.02. Diameter, we know this is the same diameter, so it's dI only. Here also dI only you should substitute. So, inside diameter of the pipe is 0.0135. The thermal conductivity of the fluid is 0.5978. You can substitute that and get HI as 6159.51 watts per meter square Kelvin. Now, after getting the inside heat transfer coefficient, you can find out the overall heat transfer coefficient using this expression 1 by Ui based on the inside area. 1 by Ui is equal to 1 by Hi plus dA by 2k into log d naught by dA plus 1 by h naught into dA by d naught. So, Hi you can substitute. dI is 0.0135 inside diameter of the pipe, and this is thermal conductivity of the material of the pipe. This is a tube wall resistance, nothing but the tube wall resistance per unit area. So, all these are resistance but per unit area. Total resistance will be 1 by HIAI. You have multiplied the AI. It is actually equation is 1 by Ui is equal to AI into the resistance, total resistance. Remember the derivation in the first class. So substitute for HI. dI is 0.0135. Thermal conductivity of tube wall material is 110 watts per meter Kelvin. D naught and dI are known. Substitute that. H naught is given as 12,000. dI is 0.0135. D naught is 0.016. Substituting and solving for Ui, we will get 4113.72 watts per meter square Kelvin. So this is the overall heat transfer coefficient. Now you can find out the mass flow rate of cold fluid. We are only given the velocity, but we know the area of fluid flow, that is inside area of the pipe. So we need to find out the mass flow rate of cold fluid or mass flow rate of water. Here we are given only the velocity of water inside the pipe, but we know that inside area of the pipe, and we know the density of the pipe. Density is 1000 and velocity is 1.5. Area inside the flow area is pi by 4 into di square. Pi by 4 into di is inside diameter is 0.0135. Okay, so we will get the mass flow rate as 0.2147 kilogram per second. This is the rate at which water is flowing inside the pipe. Now, because steam is condensing, that will have infinite value of heat capacity. So that is Cmax. So the cold water which is flowing inside the pipe is having C minimum. Whereas steam condensing outside is having infinite value of heat capacity. So minimum value is for the cold fluid, which is MC CPC. And the MC is known 0.2147. CPC is 4178. So you get C minimum as 897.02 watts per Kelvin. Now the area of one tube you can calculate. The surface area of one tube, inside surface area we are calculating. So pi DIL, pi into diameter is 0.0135 and length of the tube is 8 meter. So this will give the inside heat transfer area. So total area of one tube, inner surface area of one tube, total inner surface area of one tube. We have got overall heat transfer coefficient based on inside area. UI we have got, and AI also we are calculating. Now you have the expression for NTU, UA by C minimum, but you can use UIAI or U naught A naught. UIAI is the same as U naught A naught. If you multiply UA into AI, you will get U naught into A naught. So UI is known, AI is known, and C minimum we have calculated. So UI, AI and C minimum, if you substitute all the values, you get NTU as 1.556. So this is the number of transfer units NTU for a heat exchanger. And C we know ratio of heat capacity is 0 because Cmax is infinity. One of the fluid is undergoing phase change that will have infinite value of heat capacity. So directly you get C as 0. For a condenser, when it works as a counterflow heat exchanger, we have a reduced expression for effectiveness as 1 minus e raised to minus NTU. We know the NTU as 1.556. Substituting that, we will get the effectiveness of this heat exchanger as 0.789 or 78.9%. So this is the effectiveness of the heat exchanger. Now effectiveness can be defined as the actual heat transfer divided by maximum possible heat transfer. So actual heat transfer you can calculate either by knowing the heat lost by hot fluid or heat gained by cold fluid. In this case I used heat gained by cold fluid as the actual heat transfer divided by maximum heat transfer, which is C minimum into Thi minus Tci. But in this case heat capacity of cold fluid and C minimum are one and the same, or heat capacity of cold fluid itself is C minimum. So that will cancel out and you will get effectiveness in terms of temperature alone. So these two will get cancelled. So effectiveness is known, we have substituted for effectiveness. Both inlet temperatures Tca and Thi are known, so substituted for Tca and Thi, then we can solve for Tc0. Tc0 we will get as 67.34 degrees centigrade. So this is outlet temperature of cold fluid. So once you know the outlet temperature of cold fluid, you can find out the heat transfer using the equation Q is equal to Cc into Tc0 minus Tci. So this will give the heat gain by the cold fluid. So Tc0 is outlet temperature, which we have calculated just now, minus inlet temperature of cold fluid into Cc is the heat capacity of cold fluid. In this case, it is C minimum. So substituting for C minimum 897.02 and both the temperatures, outlet and inlet temperatures, we can solve the heat gained by cold fluid as 42,464.93 watts. And dividing by 1000, we can convert into kilowatts. You will get the heat gained by cold fluid as 42.465 kilowatt. Since it is a condenser, we cannot use the equation mCp into delta T for hot fluid, because hot fluid is undergoing phase change, it is condensing, and in that case you have to use the expression for heat transfer as Q is equal to mass flow rate into enthalpy of evaporation. So in this case it's a hot fluid, so QH is equal to mass flow rate of hot fluid into enthalpy of evaporation or latent heat of evaporation. So QH is heat lost by hot fluid, which is also equal to heat gained by cold fluid, which you have already calculated, and that you can substitute. And HFG we have already got it from the steam tables, 2645 kilojoule per kilogram, that can be converted into joules per kilogram by multiplying by 1000, and then you can find out the mass flow rate of hot fluid. Now this is the mass of steam condensed is equal to 0.01605 kilogram per second. Now this is the mass of steam condensed over 1 cube, and to find out the total mass of steam condensed, you can multiply with the 60, which will give 0.963 kilogram per second. It's a shell and tube heat exchanger. We have 60 tubes. On all the tubes put together, its total steam condensed is 0.963 kilogram per second. Every 1 second, 0.963 kilogram of steam is getting condensed. So you can usually express the steam condensed in kilogram per hour. So this is the steam condensed in 1 second. So 1 hour means more amount of steam will be condensing, and 1 hour has 3600 seconds. So multiplying by 3600, you will get the mass of steam condensed in kilogram per hour. So multiplying this with the 3600, you will get the mass of steam condensed as 3466.8 kilogram per hour. Thank you for watching.